Hello, and welcome to our Lab 3 report on the black hole orbit. In this lab, we were given a CSV file full of positions of a star in orbit around a black hole. With this information, and using Newton's second law, we were to find the black hole's mass. Based on my information, I found that black hole that I was given has a mass of 2.3882 times 10 to the 31st kilograms. To find this, we used Newton's second law. Using Newton's second law and principles involving momentum, we are able to find that F net is approximately equal to the change in momentum over the change in time. You can see that here. The change in velocity times the mass is equal to the change in momentum over the change in time. We were also able to figure out parallel and perpendicular components of the F net. And from F net, we're able to manipulate Newton's law of gravity to result in finding the mass of the black hole. We start with some initial conditions. For my black hole, we know that the star's mass is 1.989 times 10 to the 30th kilograms, and the time step is 86,400 seconds, and the black hole's position is -5 times 10 to the 10th, -5 times 10 to the 10th, 0. And again, we're able to find the calculated mass of the black hole. So how did we calculate F net? Well, we can calculate F net by calculating the change in velocities, and use the change in velocity to calculate the change in momentum. Within my code, I start by taking in the x and y values. From here, we compute the x component of velocity and the y component of velocity. Next, we go into another loop to find the initial and final velocities within each step. We do this by putting the x velocity, the y velocity, and 0 into a vector. And then we do this initial and the final. From there, we are able to find the initial and final momentum by multiplying the initial and final velocity by the star's mass. Next, we find the change in velocity and the change in momentum by subtracting the final minus initial in the velocity and in the momentum. We are then able to calculate dp dt by taking the change in momentum and dividing that by the change in time. We set this equal to F net. From there, we are able to find the dp dt parallel and dp dt perpendicular. We do this by multiplying the initial momentum times the magnitude, or dividing the initial momentum by the magnitude of the initial momentum. We are then able to get the p hat that we need to find our parallel component. Then we find the magnitude of the change in position over change in time. And then we are able to multiply that by the unit vector to get the parallel component. Similarly, we must find the perpendicular component. However, this time we can just subtract the parallel component by the F net, or the change in momentum over change in time, to find the change in momentum perpendicular. We're also then able to update the star's position and determine the mass of the black hole. We do this by manipulating the law of gravity. We must find the difference in the distance between the black hole and the star and find a magnitude of that and make a unit vector. From there, we must take the magnitude of the net force as well and find that the black hole's mass is equal to the magnitude of the F net times the radius squared, which is the distance squared. Divide that by the gravitational constant times the star's mass. We are also able to update the arrows as well. This can be seen as I run my code. Now, what does it mean? How does Fnet differ from the change in momentum over the change in time? Well, the change in momentum over the change in time is an approximation for Fnet. It is not actually Fnet. Fnet is a time derivative of the momentum, but momentum is not a force, so it is not a completely accurate approximation. However, it's close enough. What if? So what if you change with a different and use a different black hole? Well, the position of the star is the same, which will result in the same velocity. And if the velocity is unchanged, the momentum will be unchanged, and thusly Fnet will be unchanged as well, causing the black hole to be exactly the same. Thank you.